Okay, we'll start, and I assume there'll be others who'll join. I'm Ratnagari here. I will be talking to you all about the importance of sample size justification and why sample size calculation will be needed. So this is a bit of more of a lecture, but it will also cover, and hopefully by the end of it, you will understand why you need to justify your sample size when you run your study. Also, why it's important for you to evaluate that when you read papers as well, whether the sample size is sufficient and so forth, and why it always ends up being a very usual question by the panel or usual critique by the panel when they look at sample size calculation. Okay. So, and it all falls back to correctly picking the factors to estimate the sample size. When I mean factors here, it means like, what is your main outcome? What are you actually comparing? What are you actually looking at? What is the main factor? So whether it is length of stay, those kind of things. Okay, and that is the key actually in you need to use that to calculate your sample size. And then at the end, hopefully then by the end of this talk, you'll be able to explain and justify your sample numbers during your defense, like why your sample sizes are appropriate enough for you to make some sort of conclusion, and also maybe explain why that sample size is enough for it to be used in practice. Okay. So why sample size? This one has been covered. If you've joined some previous talks, the main thing, if you remember the talk from the first talk by Prof. Arvind, everything comes back down to the research question you want to answer, and then you want to test the hypothesis. The hypothesis is the answer to the research question, and then you need to then pick the right variable and mean outcome for that hypothesis, and of course, then your sample data you need to collect and what tests you're using. So it is not, you don't just calculate, don't just test the hypothesis based on just one thing. It's based on a lot of things. Okay. And so at the end of the day, it's because you want to be able to then have even enough evidence to support or reject the null hypothesis. The null hypothesis is actually the fallback hypothesis, which is that there's no difference and so forth. Okay. So this is needed. So that comes to p-value. So sample size is based off, you need to calculate it because you want to at least have statistically significant findings. And more so, you want to be able to have clinically significant findings and not just statistically significant findings. So it's important that first, statistically, the p-value has to be less than 0.05 so that you can reject the null hypothesis. And then obviously post that you need to then, you then need to be able to conclude based on the findings you get. Now, why do you want to do these things? You want to reduce, there's two types of errors. There is type 1 error, and there is where you might get a false positive, and it's known as alpha. Okay, so it denotes as alpha in a lot of the calculations. When you go and see a statistician, they will ask what the alpha value is normally fixed at 0.05, sometimes it's 0.01. Okay, and then the other is to avoid false positive. So you don't want to say that what you're finding is false positive is basically saying someone has the disease. I mean, someone who has the disease but saying they don't have it, and vice versa. False positive is when they don't have the disease, you're saying they have it. So you don't want these kind of errors happening and this can happen because it is errors can happen anywhere, right? So you want to avoid these two errors, and that's how the whole story of you want to have a powered study. So you always hear everyone telling you, is your study powered enough? Do you have enough sample numbers for it to be a powered study to represent the population and so forth? Okay, so at the end of the day, this is where you want to be able to reject the and say your results are true. Okay, so power is basically the ability for you to reject the null hypothesis when it's false. Okay. So, and in the process of it, you want to minimize the two errors, type 1 error and type 2 error. So alpha and beta error, you want to reduce it. And this is where sample size comes in. Because of course, if you do census, You're going to get everyone. You're not going to even need to worry about census studies. You don't need to worry about power because you're collecting all the data. But but you cannot be doing that you're collecting data maybe from one hospital, sometimes maybe two. And so you want to have enough samples to represent the rest of the population, but you don't need to go out to the whole population who have the disease and collect from every single person. So that's what you're trying to avoid here, so that it reduces. So that's why it's called sample, because the sampling of, I'll show you another image of it. So by default, sample size numbers will increase when you want to try and decrease both the errors. So that's when the whole calculation is needed, because you cannot be trying to collect 2,000 patients if you're not going to have that numbers in a hospital in 1 year, right? So as I was explaining, a sample is basically a small representative of the population which is out there. So, but you can't be collecting every sample which is out there, because a lot of resources will be waste, your time, money, and then you've got other things to do besides just collecting sample for your study, right? So but you want it to be accurate enough for you to test and have statistical significance first, and then clinical relevance. So that's why sample collection is done. Okay, and then a sample frame is basically the area where you're collecting this. Of course, I've given you examples here of registrar office classes, but another example is the hospital EMR system. Okay, it's a sampling frame. Okay, and so why do you sample? Because you don't want to be, as I mentioned, you don't want to be going and collecting information from everyone. You want to at least reach the target audience, but you want to do it in a way where you don't need to go to every single hospital and collect the data. Okay, so then comes back down to your collection, your sample which you want to collect. Who are you interested in? So this is when I think you guys already know that you need to know your inclusion criteria, your exclusion criteria. Who are you collecting from? Who's the interest group here? Okay, right? And then that comes down to you thinking about the process of how you're going to collect the sample. Comes down to the topic of today, sample size, and who are your participants and so forth, because that comes to that bit of feasibility, right? We always say, is this feasible? So who's going to participate? Are you going to be able to get them to actually enroll? If not, then doesn't matter if you calculate the sample size. If you're not going to be able to actually collect, you're not going to get the recruitment going. Okay. Then when do you do the samples? When the population, when can you do the entire population? When it's a very rare disease. Okay. So when the population responds to rare disease, you might then try and get the whole data. But again, that's probably not something which we advise you to do, because you're only going to probably try and get ethics from one hospital. Okay. When there is a lot of resources. So this happens, obviously, if they do collect all the data, National Cancer Registry might collect all the data in the country, right? So they will do the whole census thing, but you're probably not going to be doing it. So this is giving you a picture view of it. So your sample, your study is calculating sample size so that you can actually represent the study population, which is part of the world. Okay. So that's why you do sample size calculation. Okay, another way of you seeing it. So you're representing everybody, and rather than just doing a census. Yeah, I'm not going to go through. Okay, so maybe I will go through this. So probability is that you randomly collect samples, which is that that means you don't have any system on how you're collecting it compared. When you're doing it non-probability, that there's no system to it. It's just by convenient sampling, or by just randomly saying, okay, I'm just going to take everyone in the clinic today. So that's all not actually systematic. While like RCTs, normally you would end up collecting it systematically, because you have very clear guidelines and so forth. Okay. All right. Now comes to our topic at hand, sample size determination. Okay, so why I've put all these question marks is because these questions, when you need to calculate your sample size for your study, these are the kind of things where you need the information before you see a statistician, And I don't mean, it doesn't, not always going to be us. It could be SBM, it could be research office and all of those people which you statistician outside. If you give them any of this information incorrectly, then the numbers which they're going to tell you will not be correct. And then when you come and try and defend it here, you're going to be asked like many questions. So to avoid that, it's always better to be very clear with what your primary outcome in your study is. Okay, so whether it is that you're going to look at length of stay, whether you're going to look at bleeding rates, or anything like that. So what is your main outcome measure? It should be somewhat measurable, even if it's a percentage difference, whether it's a mean difference, median difference, whether it is, if it's ROC curve, whether it's positive predictive value, the positive pickup rates. So you need to be very clear what is your main outcome and what is the matching measurement of that main outcome is, okay? Then you also need to know whether you're dealing with one group, two groups, three groups, because based on that, your sample size will differ. And the calculation, sometimes if it's two groups, a different formula is used compared to when it's a single group. And when it's three groups, you might need to calculate for one, and then they might times it and so forth. And sorry, you have a question for me? No? Okay. Okay, so study design. Then you need to know your study design, whether are you trying to prove something to be better than the other, whether you're going to prove that one is actually poorer than the other, or are you trying to prove they are equally they are equal to each other, okay? And as I've already mentioned, you need to know the type of data you're dealing with. Are you collecting your main outcome, especially? Is that data going to be collected as a continuous variable? So that means you're going to then represent it as a mean or median, or are you collecting it as numbers, so it'll be as a percentage, or are you collecting it as another thing where you might collect the data and present it? So the usual ways are mean, median, or percentage, okay? But sometimes you might collect data and it may be like a scale, right? I'm not scale, sorry, like it is actually in a category. So like mild, moderate. So, or it could be like, the pain score, it's actually yeah, it is a scale 1 to 10, but however you categorize it based on the smiley face, it might end up pain being at 10, but then you group it as high, that it is severe pain and so forth, right? So you end up grouping it. So you need to really know what is your final output going to be of that data. That matters actually when they need to help you, or when we need to help you calculate sample size. Now that comes then to how the reason is because how you're going to analyze this. Is it going to be logistic regression, t-test? T-test is for mean, right? And logistic regression is when you are dealing with predictive models and so forth. So, and if you're looking at a diagnostic test, COVID test, ROC curve and positive predictive value, those things. So the analysis matters. There will be a individual stat talks coming after this for all of these different tests. I think Tanya already covered the t-test, but there'll be even the ROC one, which I think done by Dr. Shah later this year. Okay, and then you need to know whether you are going to be representing significance using p-value or effect size, and sometimes you might do both. And whether your study is just a pilot study or not, and it's just a feasible study. I mean, pilot study is normally done to test feasibility, not really to test statistical significance. So the sample size calculation for pilot studies are different compared to some of the other sample size calculation which needs to be done for the other kind of study designs. Okay, before I continue, I first need to see who is here. Okay, there's 13 of y'all. Before I continue, can I first get to know a little bit about your studies? Okay, well, it's not 13, there's 11 of y'all. Can you quickly tell me, each of you just unmute and just tell me what your studies are about? Not about, like, what is your main outcome? So, like, answer some of these questions. What is your primary outcome? And what is your Yeah. So, and what is your study design? Yeah. What is your outcome, main outcome comparator? Or you can put in the chat. How about that? You put in the chat. I just want to get an idea because then I can see whether the content which is coming after this that is covered, and if anything's missing, I can try and add it verbally at least. Okay. Yeah. Can you put in the chat if you don't want to unmute and tell me? Just your main primary outcome. If you don't have a study yet, you can say no study yet. But if you have a study, I want to know what your so your primary objective, what is it? And what's the measurement? What are you comparing? Also, you can unmute and tell me if so far anything which I said is unclear, and I can clarify for you.
Hi, Prof. Sue here.
Hi. Yes,
Hi.
hi.
So I would like to how to say it,
Ask.
mention a bit about my study. Actually, my study is about using bioimpedance analysis. The primary outcome is by looking at phase angle, which is a measurement by angle and 1 decimal point. And actually want to prove that it's a feasible nutritional marker, and comparing the two groups of population. I mean two group of participants. One group is under control with the standard dietary counseling. Another one with the ONS nutritional support. So the main outcome is to compare the mean difference in the phase angle, means in order to able to calculate the treatment effect size also. So yeah,
Okay.
the one
Can
will be under
I clarify? Yeah. So it's just 0.1. How is that going to be something which is impactful if it's just 0.1 of a difference?
I see. There are studies that improvement of let's say 0.1 degree, there will be a reduction in fat mass by body composition, and also increment of muscle strength, and also increment in muscle mass, skeletal muscle mass to be specific. So it represents I mean, any increment from the face angle, it represents the increment of body composition that will help to, how to say, it will improve nutritional status. Yeah.
Okay, so your actual so your study actually is that you have you're going to give it's two groups. One is getting different nutrition compared to the other, or
Standard one, which is
stand
dietary
the
counseling.
standard.
Yeah.
Okay, and the
Then
other
the other
group.
one is counseling plus with the oral nutritional support, which will be supplying protein supplements.
Okay, so another group is going to get a protein
Extra.
supplement on top
Yeah.
of the standard of care. Okay, fine.
Correct.
So it's like a control group basically, and yeah, so it's a
It
case
seems
control
to be
group,
a
right? Yeah.
superior design. Yeah.
So superior studies. So then we will, so okay, that's all fine, but that comes back down to what is the difference. So your main outcome you're saying, but so you're saying your difference you want to see is just 0.1 difference, is it? That you're hoping at least the one where don't you think 0.1 difference is very small, that
Yeah.
of a difference? And
Yes,
why are
correct.
you going, do you have the reference paper where it says that that is enough?
0.1, that is enough. I mean,
Yeah, you
enough
don't,
in the
so
sense of the p-value.
yeah, in terms of no, not just the p value, clinically, clinical relevance, right? Why is that going to help? How do you know that's going to help the patient or patients eventually? So I would actually rethink about what the difference you want to see. Unless you can justify 0.1, actually doesn't mean 0.1. It actually means 0.1 on that. But why do you want to go with that instead of looking at something of known variables like body weight or waist? I think there's also one machine which actually measures about the body composition. There's a machine, right? Are you using
Mm.
that? The one where they stand
Yeah,
on that machine?
it's a machine. It's a machine, yes.
Yeah, but that machine, it shouldn't just come out with 0.1. It comes out with like a whole lot of things. It should tell
Yes.
you that there's an that once it actually, there's more to then, it's not just it's not just a reading. It shouldn't be a
No, no.
mean. It should be actually what your output there. I don't think it's a mean. I think it's a percentage. You better check on that. It's a percentage. That means a percentage of there is improvement in body mass in terms of the distribution of protein ratio, actually ratio of protein fat distribution is 20, 30, something like that, if I'm not mistaken. So that's what you want to see. And then maybe another thing which you'll assess is the BMI or something like that,
Yeah,
right?
yeah.
Or
It will
waist
appear.
height ratio. Yeah, waist height ratio as well. Those are the things where it's measurable, where you can actually say some things than just what 0.1. Can you re-look at your okay, so maybe your primary outcome, fine. I think your design, all of that is okay. Superior is fine. But I really think your output style, uh, you need
Mm.
to think again. I think it should be percentage. It shouldn't be 0.1. Okay. And then post
I
that,
think percentage would be a better idea. Yeah, yeah.
yeah. And reference paper. So reference paper, you obviously one is standard, right? So you would have the reading a already known improvement, like a known improvement in terms of that reading, the percentage reading of when if people were on the standard regime. So you might want to say that you want to see at least what 20% better. So the other one should be kind of postulated that you at least want to see a 20% better. Once you go give them protein thing, you will think that they might be better by 20% or 30%. That you decide with your supervisor. Okay, that's
Okay.
what I
Mm.
recommend. Okay,
Okay.
so
Thank you.
now with that example, there is a RCT way to calculate when it's percentage. But anybody else before I continue, can I get a few other people telling me what kind of study? Okay, there's some things in the chat. What other studies do you do? 1-year patency, ABF, okay, between scoring, high, also an RCT. Sorry, give me a sec. 1-year patency. Another one is to do with Hancock incision, observational study. Primary outcome is the rate of catheter, okay, at 30 days, all right? And then observational modified technique between balloon, scoring of balloon and high pressure balloon.
Yeah.
Okay,
Good afternoon, Prof.
can you explain? Yeah, hi, good afternoon. Can you explain to me
So
that
basically,
bit? Yeah,
I just want to confirm. Basically, my study compare the outcome of patency of the fistula, whether it can be used or not, between two groups. One is
yeah,
using scoring balloon, and the other one is using high pressure balloon. Basically, it's two types of balloons where we
okay,
do the same procedure using two types of balloon, and we measure after 1 year whether the fistula can be used or not.
okay. So okay, so what is the improvement you want to see, or what
We are
is the
looking
known value?
the usually for the high pressure balloon, the patency rate after 1 year is about 40% of
Okay,
patency, whereas in scoring balloon in a pilot study it's about 80%. But the pilot study is a single arm study, observational
yeah.
study lah.
Okay, so you have
So
those two references, right? So that's what
yes,
you need to
yes,
use in your so they're percentage then, right? Both are
right,
percentages. Okay, and
yes.
it's RCT. I'll be coming now to one example of what you can use when it's an RCT. Anyone who's doing other kinds of study models besides RCT, I saw there's not observational study. Anyone doing ROC? Anyone here doing ROC related studies or logistic regression? Or you're not sure yet what kind of analysis you're doing? Okay, never mind. At least I get an idea of the studies which are coming up. So what I'm going to present will be useful. Okay. Again, there are many ways of calculating sample size, and there's different formulas for different for all of these things. That's why I'm listing this to you, because one thing is when you go to the statistician, I don't know whether any of you all remember the whole computer code. Yeah, the one date rubbish in, rubbish out. I don't know whether you know that DOS code, MS-DOS times when they say rubbish in, rubbish out. So the same thing applies here. You can have a formula, but if you give the wrong numbers to the statistician and the wrong study idea of what your main outcome is to them, whatever they calculate, it is correct according to what they are told. So the idea of my talk here is for you to first understand the basics of why you need to justify sample size, and how it's because it's trying to represent a bigger population. Okay, all of that. But more so, when you need to calculate sample size for your study, you need to go to them before you don't just make the appointment with the statistician at the research office or whoever you're going to see, even if it's outside. You need all of this information and publish papers in similar published papers with the numbers, the right numbers. And who can help you confirm whether the numbers are right or not is your supervisor, because they will know whether the numbers make sense or not. Once they say, yes, okay, this is the right reference paper, this is the right mean outcome, then you see the statistician to use the form. They have all the formulas. Once you show them the right things, then they can calculate based on what you're telling them. But if you go with the wrong reference paper, it's going to give you the wrong numbers. And then you're going to go back unnecessarily, wasting your time actually, trying to recalculate the sample size many times. So go with the right numbers from the beginning. That's the whole point of my lecture today, is for you to understand that actually, if you go with the right numbers, right reference paper, or right audit data, because sometimes it may not be a published paper, it might be just that local, you've audited it, and then you have those numbers from that, and that's what you're using to calculate the sample size. It's still right numbers, right? Because you have done an audit and then you're using that to calculate. Okay, so that is the more better way to go with things, or you're basing it off with some pilot study or something like that. Or if there's no studies at all, you might yourself do the pilot first to get those numbers, and that could be your study itself. Okay, but now coming back to this. So I think at this point you understand that it is important that you go with the right. You cannot give the statistician one study is a mean and the other one is a percentage. It has to be or anything like that. It has to be standardized. Okay, what you give them. Okay, that's the other thing which I need to highlight. Why I'm bringing this effect size, sometimes you might not go with p-value, and people might say, especially when it's very small, rare diseases, you are trying to see a difference. Sometimes they do say p-value because it may be statistically significant but clinically not relevant. Then they want you to justify it further with what kind of effect you see. How much better is it? So effect size, you can have a small effect where you just see a mild improvement, or you could be a large effect size where you see a greater improvement. So this also where the whole superior, inferior thing comes in as well. So sometimes statistician might suggest back to you that because you are dealing with such small numbers, maybe do your analysis and your sample size justification using effect size rather than p-value. So if they suggest something like that, again, run it through with your supervisor, post that, and see whether your study can be based on effect size rather than p-value. Okay, and which actually you can there are studies which are published based on effect size, reporting effect size, and rather than p-values. Okay. Now, remember, I just told you that this nonogram was from since 1982 is for RCT studies. Okay, so this is the published book or reference, and this is a quick formula based off that that reference, and it can be done for percentages. It can be done for mean values. Okay, so not really median values, but for mean values, and if you're dealing with means or if you're dealing with number and percentages. Okay. And as you can see, the power is 80%. This is a formula. The one which you're going to calculate is the standardized difference. And what happens, so this is, if it's a mean, so you got your two mean values from a previous study or a pilot study, and you get the standard deviation from the previous study as well, and you kind of calculate it. So I'll show you an example soon. So like example here, children are given treatment X, okay, and they want that the lesions last less than 72 hours. So this is a randomized trial, placebo and control. So something like what you know how you just said you've got two different treatment. One is nutrition, and then the other one is nutrition and you're giving protein. So just take it like that. Okay, and then you kind of determine how you're going to administrate it. And then see, as I said, it's very important that you know what your main outcome is. In this case, they're saying the main outcome is looking at the duration of the oral lesion. Okay, how they're going to measure it. And then based off that, you will calculate the sample size. So in this case, I've kind of given it as 90% power, but that's just me giving an example, but normally 80% power is enough. But at 90%, your alpha error is 5%. So this is always fixed anyway, okay? This is fixed. 80% normally is fixed. Sometimes you might say you want 90% power, but all of this is normally fixed. The only thing where you need the reference paper actually comes in with this thing, the difference, right? What difference you're going to see. So that's when you need to get the reference paper from outside, a previous pilot study, local audit data, or similar studies in other regions, or two different reference paper of treatment of treatment A, reference paper for treatment B, and then you kind of use those numbers, and then you say I'm running the RCT, so then you get those reference paper. It can be a mean value from there, a mean value from here, or it could be a percentage from there, percentage from here, and that's what you plug into the formula here. So this is normally you don't need to use this formula. You can actually tell the statistician it's a RCT, but you have to make sure you give them the right mean difference or the right percentage difference to them. Okay, I'm not going to run through the maths, but I will be sharing the slides so you can run through. So what happens here actually is with the mean difference, it is then calculated, right? And it then says, it then ends up telling you that it's going to be 0.50. This math is needed because from that, it matches, you see the 0.5, the standardized difference is from here, 0.5, and 90% power. So this is power, 80% power is here, 90% power is here. So you just draw a line and it's telling you that you need a total of 140. Okay, sorry, let me just go back. I thought it has a slide. It doesn't have it. Okay, yeah, here it is. Sorry, not 140. 160. Okay. So then if you use the formula, using that, so the standard difference of 0.50, okay, 0.5 and a power of 90, you need a total of 160, 80 per hour. Okay. That's one example. Now, remember I told you that was a mean example of two means. What happened? You are dealing with percentages. Okay. So this is, and you want 80%, and your confidence level or your alpha error is allowed is at 5. Okay. So then how do you do? So this is the formula for it. Okay. So or your population 1 is the prevalence of the actual infection, and then what do you expect? Okay, it's the other percentage. Then and keep in mind when it's P over a line in this formula, it's actually an average of the two percentages. You calculate all of that, you do all the maths. I'm not going to go step by step how you calculate it. The whole thing is done, and it will come up with a standardized difference of 0.58. Again, go back to the graph. This is how they used to do it manually before. By the way, now you can actually do this using online software. So I'll show you one. But if you go to statistician and you don't even need to give them the 0.50, they are doing that for you. What you need to do is to give them the right numbers, these two numbers, okay? And then the other case number, the mean different numbers, okay, with the standard deviation. So that's why I mean the reference paper used is very important, because you give them really the incorrect numbers, everything downstream will be wrong, okay? And again, here ends up telling you need about 85, okay? Yeah, looking at 58, you draw the line across and 80% power, and you need about 43 per group. Of course, this is not factoring in for, especially for RCTs, they normally ask you to factor in at least a minimum of 10% dropout rate or 20%, right? So this is just without that. So you can add on another 10% or 20% of this 43, and maybe you might make it 50 per arm. Okay, just giving you an idea. Oops, let me go back. All right, so I'm still showing you examples for RCTs. Again, this is the same graph. This is a quick formula. So as you can see, it actually roughly gives the same thing using this formula. So you don't actually need to, after you calculate the standardized difference, getting that number, you can just use this formula if it's 80% power, and you don't need to actually use that graph. Okay. Now, this is an online system, okay, and doing the same thing, putting in the numbers. As I told you, you enter the alpha error, it's already fixed at 0.05. Okay, the desired power is also fixed at 0.80% power, 0.8. Okay, and then it just you select here, calculate sample size, okay, for a fixed power. And by clicking that, you end up actually, and then you put in your proportion 1 and proportion 2, and you calculate, it'll tell you you need 62 per arm. Okay, so each group will need 62. Okay, it's based off this reference, but this is the web link. Now for means, sorry, not means. Another way, the reason why I have this as well, I find it useful, is a lot of people, of course, now we encourage you all to make sure you calculate your sample size correctly from the beginning. But sometimes you might do a study, and at the end, you find that you are not powered. You can actually work out whether your study is powered enough. As you can see at the end, this study with these numbers, it ended up saying that you are sitting at a power of 0.75. Okay, so you can actually do it the other way around as well, by saying you want to calculate the power with a specific sample size. So you type in the sample size, you type in the fixed thing, you actually leave this blank. This is blank. You fill this up, you fill everything else up, and then it will tell you that actually your power is only 75%. So it's not 80% power yet. So this is working it backwards. I used to have this for the very 2010, 2011, 2012 batch, because they used to have to justify that they are not powered yet. Okay. So that's an example of an online website which calculates for RCTs. There are actually papers which are out there explaining the difference between the different study, one which is superior, whether one is equivalent and everything. So this is a reference paper. I will share all of these reference papers through Nadia, and she'll send it to you all. But I'm not going to go through the content of this paper, but this is a good paper to read to understand more. And it's not only useful for you calculating sample size for your study, it's also useful for you to read to at least as when you want to practice for your Viva and stuff like that. Okay, so, and again, remember I already told you that calculation, sample size calculation, the ones which I'm showing you this now, that is all for superior. Okay, even that online one which I'm showing you is for superior. But the minute when it's non-inferior and equivalent, there's different formulas. So you don't need to go and memorize and do the calculation yourself unless you want to learn and you like doing maths. But you need to be very clear to the statistician whether it is superior, whether it is non-inferior, whether it is an equivalent study, so that they can use the right formula for you and help you calculate it correctly. The reference paper will be still the same. The reference paper for group A, you have that reference already, right? It's the same. The difference you want to see, also you can tell them, and they will then work it out. The difference then, if it's equal, if it's non-inferior, you want to show equivalent study, you want to show that it's the same, it'll be the same numbers, right? You actually need, it's not 30% better or 30% worse. Okay, it is actually equal. So it's the same numbers. So so they will already know that it's the same numbers in each group. You just want to show A is equally as good as B. While non-inferior is you want to show that B, rather than showing B is better than A, you want to show A is better than B. Okay. And sometimes you need to do that because equivalent studies because you want to give more options to the patients. Non-inferior is because you want to now debunk the current practice, standard practice. You want to debunk it because it's been always said to be superior, so you want to debunk it. So like you want to take it off like non protein pump inhibitors or something like that. You want to say you don't need it for certain, or you want to take out the ventilator and stuff like that. So that's when these kind of non-inferior studies come in. Okay. This is further explaining it, another reference paper on step-by-step how to calculate. I'm just sharing this information. And as you can see, the hypotheses are different for different things. So again, statistically, a study being statistically more superior is different from a study being clinically more superior. So you need to remember that. So if something can be statistically significant, does not mean that it is clinically significant. So that is the point of this table here. Okay. And this is not just for RCTs. This could be any kind of study model. Okay. Now coming to, so all this while I've been talking about to people who are doing studies who are like RCT designs, right? What happened? Your study is actually just looking at predictive models, looking at studies where you are dealing with survival models, looking at Cox regression or logistic regression and so forth. Then there is actually already reference papers which are out there, especially this particular paper by Podizil, who has already said based on the number of factors you're looking at. Okay, so each factor at least you need 10 a number of 10. So if you're going to look at factors age, race, number of operations, bleeding rates, all this, each of it is a factor on its own, right? So each of that, you need 10, 10, 10, 10. So all you need to do is you need to be very clear how many factors you're looking at. And then based on that, you times by 10. So if you're looking at 10 factors, you need 10, so you need 100. Okay, so with 100 patients, you can look at 10 factors. Now keep in mind though, sometimes some factors, if you have subcategories, then it may not, each of it is then considered a factor on its own. So you need to actually you should explain very clearly. You don't really need a statistician, you can actually reference this, but explain to discuss with your supervisor carefully what are the factors and see whether that factor is a standalone factor or it actually ends up being actually in that factor there's two things to it. So, but this is referencing this and calculating based on this is sufficient enough when you're doing your analysis output, your main analysis and your main outcome is using logistic regression. And when I say survival model, I don't mean Kaplan-Meier, I mean Cox regression, right? So any kind of regression, okay? You can actually go with this rule of thumb where for every variable you're looking at, you can have, you just need 10 patients. So if you're going to have 10 variables which you need to look at to predict, you then need 100, okay? Understand? And you can either get a statistician to confirm it, or you can even use online softwares like GPower, right? Now, pilot and effect size, so that I put it next to each other because most of the time when it comes to pilot studies, you can either go with saying calculating based on the effect size rather than p-value, which you don't, or you can just go with this reference paper. Okay, this is a published reference. You can go and read the full paper. I'm not going to go through the content of every single paper which I'm putting here. Hence, I'm putting the references here. When I share the slides, you can go and read the full content. But they've already said, normally pilot studies, actually you don't need to calculate sample size, but nowadays you need to justify why that number is enough for your pilot. So there is general recommendation is each group you look at, whether it's RCT, whether it's just an observational study or anything like that, 30 per group is enough when you're doing a pilot. But you only can do a pilot study when there's no study in that area done before or no comparison between those two groups that have been done before. But again, sometimes if there's already one arm, you can kind of still do a bigger study. But if you think nowadays, ethics actually, when it comes to more treatment-related stuff, they rather you do a pilot first before you actually do an RCT. So in a way, nowadays, pilot studies are encouraged. And remember what I said, pilot studies are not done to look for statistical significance or clinical relevance. It's first looking at the feasibility or efficacy, those kind of things is when you run a pilot study. Okay, so it's not done to come up with a clinical conclusion yet. It's the first step before you actually do a bigger study. And you can do that as a project when there is justification of why you need to do the pilot one first. Okay. So numbers there is, others have suggested even 12. You don't even need as 30 as 12. And this is the reference paper for it. So if you're coming and you're defending and saying you're doing a pilot study, first you need to defend yourself by saying why a pilot, you need to do the pilot first. As I always said, it is because you need to do a pilot first because ethically, it is, don't just say what I say, but back it up based on ethics. This is in order for me to for this to be a full on to be a RCT, I need to first have justification that this study is going to be safe. Hence, I'm doing a pilot study first. And in order for me to do this, I'm not going to do large numbers first. I'm going to go with small numbers as 12 because I first need to see the pattern. So, and from a pilot study, you can see patterns, you can see trends, and all those kind of things. Okay. And then based on the pilot study, just like how you would do an audit, pilot studies will then give you reference numbers or reference values, which can be used to calculate sample size for the bigger RCTs. Okay. Next are these two things. Okay, I don't want you to confuse both. Let me explain this one first, then I'll explain that. So here is when you are doing, if your study, I don't know, none of you actually brought this up, but I might as well share it. In case your study is looking at doing ROC curve or looking at predictive values, positive predictive values and negative predictive values, looking at ROC curve and looking at diagnostic tests, or this is something which they would have to justify sample size needed for a test. So if it's one test, you then can calculate it. So as I already told you, the errors are normally fixed. Okay. The area under the curve is what you want. So area under the curve, you already know a good area. This is already normally fixed. You can't go with 0.6 or anything like that because then it's no point. It's not a good test if your area under the curve is below 0.7. Actually, the best is actually to fix it at 0.8 because then you know it's a good test, right? Then the value which you need to find are the ratio. How many do you think you are going to be in? Do you want it to be equal? 2 to 2, 1 to 1, those kind of things are what you need to discuss or find reference from previous papers or discussions with your supervisors. And again, what is it, the standardized difference which you want to look for? So these two numbers you need reference. This one is from that curve itself. If you've seen ROC curve, later I think when Dr. Shah explains to this might make more sense, but the ROC curve, you should probably want to keep it not below 0.7. The best is actually 0.8. So all of this is fixed. This is where you need to get the numbers. Once you get those numbers, it will then calculate how many cases you need, and then it'll tell you altogether in how many groups you need to be able to pick up the enough positive cases and rule out negative cases. Okay. So this is when it's just to do with one. What happens if you're comparing two different scoring systems? Okay, so this is a scoring system, just one, and you're just testing it. But what happens, you have two different scoring systems and you want to compare the two different scoring systems, then you actually need to go with comparing two. So the scoring system one, its curve, scoring system two, or two different diagnostic tests. So diagnostic test one, what is the area under the curve is supposed to be, and 2. So if you can see, they already started to put it at a higher 0.9 and 0.8. You also need to know the correlation. So correlation you would get between those two tests. What do you think the fixed values are? So again, this is where you need to get the reference papers in. Okay, so you can actually fix everything else. The one where you actually need is the to get hold of the value here. Here, obviously, they said they want it to be equal. to show at least both are equally as good, and hence they fix it at 0.4. But sometimes you might want one to be better than the other, like superior, then you might actually fix one at 0.6 and 0.4. Okay, so again, these are the links for it. You can test it out, but if you put in the wrong numbers in here, you're not going to get the right numbers here. Okay, this is for if your analysis is going to be RC curve, predictive diagnostic test, positive predictive value, looking at two different scoring systems, and you want to see its predictabilities, how well it can pick up rates are, and all of that. This is the better sample size method to go with. Okay, so I'm coming to the end already. So in summary, right, there are many things there are many ways of calculating sample size. These are all the published papers. Remember just now I showed you logistic regression and a Cox regression. So that's the paper which I'm showing you for the 10, which says what numbers are needed. Similarly, there are each different analysis which you use. There are different ways you can justify your sample size. I don't think I need to sit here and show you how each of it is done, because my idea of the talk today is more for you to know that that actually all it comes down to is you knowing what your main outcome is. Okay, so take home message, what your main outcome is, knowing what you are going to so your main outcome, and also how you're going to analyze it at the end. Which are you going to do? Sensitivity, specificity? Are you doing logistic regression? Are you doing one-way ANOVA? Are you doing chi-square tests? Okay, that is what you need to know. Are you doing correlation? Then it's a OHD, so it's different, right? Then you calculate the sample size based on this. All right. Okay, I think that's it. I got a few things. Before we end, I will take some questions. Yeah, give me a sec. Are you all there? Okay. Before we end, I'll take some questions. Anything you want to clarify in regards to the talk or your own studies? The other thing is, next week's session is not me giving a lecture. It's actually me giving everyone about a 15-minute slot. Keep in mind, it's only 15 minutes. So if you want some guidance, I don't know at the end whether we will calculate your sample numbers for you if you need, or if you want to check your sample numbers are correct, that is probably more doable. But you want me to calculate, 15 minutes not enough, but what you could do is at least get some direction on what to do to get the right numbers and check and I can make sense of whether what you're saying, your sample size, that you're justifying it correctly or not. Okay, but there's only 8 slots, so you can let Nadia know if you need it, and then I will see each of y'all between 3 and 4, each of y'all 15 minutes each. Okay, but come with your reference paper, come very clearly with what I've asked you. Maybe I'll send that these slides will be shared, but remember that slide where all those question marks, please come with all of those answers and write reference papers so that we online. I'm not meeting you in person, I'm meeting you online, so you can share the paper ahead or something like that through Nadia, and we can meet then. That is what the next week's session is about. All right. Now, questions? Any questions now